Okay, hello and welcome to our first video session in Unit 4. This is water as a solvent. Water is the number one solvent that we are going to use in chemistry. And what is a solvent? That's a great question. A solvent is the substance that dissolves another substance, such as a solute, in order to make a solution. All of these words kind of sound the same, so make sure that you're following in your study guide and writing down these definitions, and pause at any time if anything is unclear for you. Remember that another term for a solution is a homogeneous mixture. So for example, when we dissolve table salt in water, salt is the solute and water is the solvent. And the resulting mixture is a solution. So if water is the number one solvent, that means it can dissolve many different substances. There are other solvents too, of course, but the one that we're going to deal with the most frequently is water, which means it's really, really important. So why is water such a great solvent? The answer is within its molecular structure. So let's go back and review a few things. Let's review how to draw Lewis structures using the TV method. First, what we're going to do is total up the number of valence electrons contributed by all the atoms in the molecule. Let's make a list of the atoms that are the elements that are present. We have hydrogen and we have oxygen in water. Next, we're going to write the number of atoms that are present in each molecule. Hydrogen, there are 2, and oxygen, there is 1. Using the periodic table, we can determine the number of valence electrons that are contributed by each atom. Hydrogen, of course, only has 1 electron. Oxygen has 6. We count from left to right across the row, it has 6. Multiply across and add them together to get your total. We have 8 valence electrons to work with, and this is V in the TV method. Next, we're going to lay out our atoms symmetrically, H, then O, then another H. Remembering the octet rule, all atoms want to have 8 valence electrons, except for hydrogen, which only needs or wants 2. We're going to give each atom the electrons it needs to satisfy the rule, ignoring how many electrons we really have to work with. Remember that the electrons in between atoms are being shared and they belong to both atoms. Now we count up the number of electrons needed to make them all happy, and in this case, it is 8. And this is T in our TV method. Next, we subtract T minus V to determine if we need to make double or triple bonds. 8 minus 8 equals 0, so our structure is good as is. Remember that Lewis structures are two-dimensional representations and do not tell us anything about the shape. We can redraw this molecule using sticks and lines instead of the double shared pair in between there. So that's our final Lewis structure. Let's go back and also review VSEPR, valence shell electron pair repulsion theory. It's important to know the shape of these molecules because these can help predict properties and behaviors. Based on the correct Lewis structure, which we have just drawn for water, a water molecule has 2 areas of bonding and 2 lone pairs, which gives the magic number, technically a steric number, of 4, which makes this a bent shape. The bond angle here is 105 degrees, roughly. So we're just going to redraw this as a bent shape. All right. Okay, we've got the Lewis structure, we've got the shape according to VSEPR, and now let's talk about electronegativity and polarity. All of these things are connected. We're still thinking about that question. Why is water the number one solvent? We're getting there. Electronegativities are important because they can tell us something about the electron distribution in covalent molecules, whether that's even or uneven. Atoms that are more electronegative have a tendency to pull the electrons in towards themselves, partial negative charge. Atoms that are less electronegative have a tendency to get their electrons pulled away from them, hence a partial positive charge. If we look at 2 different atoms' electronegativities, the larger the difference, the more polar a bond is. The smaller the difference, the more nonpolar the bond is. So polarity is going to be something that we refer back to quite a bit throughout the year, so it's a really important concept. We're going to look up the values here for oxygen and hydrogen using this periodic table. Oxygen is 3.44, hydrogen is 2.20, And if we subtract these two, we get 1.24. Looking down below at our electronegativity chart, this means that the OH bond, this difference, 1.24, falls in the polar covalent bond type, which means that this is a pretty polar bond between oxygen and hydrogen. We can represent these polar bonds with arrows pointing towards the more electronegative atom. And because there are two lone pairs on the central atom, the molecule as a whole is also very polar. Okay, so what have we learned so far? Water is a very polar covalent molecule. Another way to represent the polarity here is with colors. The red at the top, where the oxygen atom is the partial negative, and the blue towards the bottom is where the partial positive is. So you can see that the colors are pretty strongly opposed here, so it's a pretty polar molecule. Have you heard of the phrases like dissolves like and opposites attract? This is going to help us explain why water is a polar solvent. So we're going to watch a short animation and see what that means more closely. And at any time, replay it, pause it, write some things down, draw pictures, because it's a really important concept.
An ionic solid dissolves in water because of its polar nature. Notice how water molecules become attached to the ions of a sodium chloride crystal in the process called hydration. Positively charged sodium ions attract the partial negative charge of the oxygen in water. A similar attraction occurs between negatively charged chloride ions and the hydrogen atoms, which have a partial positive charge. These interactions loosen the attractions between the ions in the crystal, dislodging them from the crystal. Additional water molecules surround the released ions, insulating them from attraction to other ions.
Okay, so a lot of important concepts there. The water molecules, because of their partial positive and partial negative ends, were pulling away the positive ions and the negative ions in the salt crystal. That is what dissolving means. Opposite charges are attracted to each other, hence the phrase like dissolves like. This is what we call dissolving. So from this we can write balanced equations for the dissociation of NaCl. And this isn't a chemical reaction here. It's just dissolving in water. It's not reacting with the water. So all I need to do is break it apart. Sodium chloride as a solid dissolves into sodium ions, which are positively charged. They're aqueous because they're dissolved in the water. And chloride ions, which are negatively charged, also aqueous. It's as simple as that. It's just a dissociation equation. Okay, so does this work for non-ionic compounds, such as covalent compounds? It depends. We're going to look at something like ethanol. The carbon-hydrogen bonds here, we have a lot of them. These are going to be non-polar bonds. The electronegativity difference between carbon and hydrogen is not great. It's only 0.3. You can refer back to the periodic table and look those up again. But these are going to be non-polar bonds. But we do have an OH group on here, which does look like a part of a water molecule. This OH group is going to be very polar. The oxygen and hydrogen is going to have an uneven distribution. So, even though one end is nonpolar, the other end is polar, and this is what's going to help ethanol dissolve in water. So we know that polar things dissolve in polar things, but do nonpolar things dissolve in polar things? Remember that phrase, like dissolves like. Let's look at oil and water. So we have a basic structure here for most oils and fats. You can see right away that there are a lot of carbon atoms attached to other carbon atoms, which are attached to hydrogen atoms. So this carbon-hydrogen bond, again, is very nonpolar, and there is a lot of them. We know that oil is going to be nonpolar. Does oil dissolve in water? No, it does not. We've seen this multiple times, that oil sits on the top and water's on the bottom, so they don't mix together. But oil can dissolve in other nonpolar things, such as benzene or paint thinner or other nonpolar molecules. So like dissolves likes is still a very true statement in that sense. Okay, so have we answered our question, why is water the number one solvent? Let's review. There are so many ionic compounds and polar molecules that water is such an important solvent to dissolving them. It's a bent molecule. We've established that because of its Lewis structure. It's polar because of its structure, polar bonds because of that high electronegativity difference between the atoms, which means uneven pull of the electrons. Like dissolves like is a very important rule here. And then we learned about dissociation equations for ionic compounds, which just means that they break apart into their respective ions in water. So this is an important concept. We're going to be talking about it all year long. Water is a polar solvent, and it is very useful to us here in chemistry.